All right, guys, welcome back. Again, your Professor Mr. Boone here, back with 6-7. And we're going to be looking at polynomial functions. We've looked at a lot of these so far this year. And good slide to refer back to is kind of visualize what these things look like. We should know when it's linear, quadratic, cubic. We know that one. That's the oh no you didn't girlfriend graph. We love that one. And then, of course, the quartic and quintic. And so we're going to kind of investigate. The biggest thing is kind of looking at end behavior. How was it ending? And one of the things that you notice is that the odd degrees, 1, 3, and 5, what you're going to notice is that the end behaviors, they're going to be going in opposite directions. All right? Where the evens, the end behaviors, where they're pointed, are both going to both be up or both be down. We'll kind of talk about how you can tell when they're going to do that. And the best part is, if you're ever in doubt, Desmos, graph it, see what it looks like. Picture sometimes is really helpful, and I encourage you to use that anytime you're not quite sure. So some notation that we're going to talk about here is this end behavior notation. It says when x approaches infinity. So let's just kind of draw our axes out here again. Here's our x-axis, here's our y-axis. Now, when we say x approaches positive infinity, here's where positive infinity, so really what that means is as we go to the right, what's happening? Now, negative infinity is this way on the x-axis. So if we ever say, hey, when x approaches negative infinity, what we're really saying is we're going to the left. All right, and then what we're going to talk about, so we have x and then f of x, remember that's really the y-axis. That's really what y is. And so if it's going up, we say that it goes to positive infinity. And if it's pointing downward, we say that it goes to negative infinity. So keep that in mind as we talk about this. Kind of a weird notation, but once you kind of get the hang of it, it really makes a lot of sense. Okay, so again, another slide here that kind of shows that a little bit is this, as you can see, as x approaches positive infinity. So as we're going to the right, you can see that the function is going up to positive infinity. Whereas if we said, hey, we're going to negative, x is going to negative infinity, we're going to the left, you can see that the function is pointing downward, and so that means it's going to negative infinity as well. So this is kind of a nice reference on the quadratic function here and here, and then the cubic function here and here as we have it. So, all right, let's try a couple of these, and then again, we have a nice little worksheet that should help kind of bring it home for you. All right, so identify the leading coefficient, degree, and the end behavior. So here's what we're talking about. This is in standard polynomial form. So the leading coefficient here, basically we want to look at, is it positive or negative? So it's negative. And then the degree here is 4. All right, so now we kind of get a picture of what those graphs look like. And if, like I said, if you're not sure, graph it on Desmos, see what it looks like. What you're going to see is a graph that looks something like this. All right, and it's an even function, so we got to describe the end behavior. So here's what we'll write. We'll say as x approaches positive infinity. So in other words, as we're going to the right, this is q of x, that's our function, q of x. Well, as we go to the right, q of x is going down. That means it's going down towards negative infinity. All right, and then we're going to say as x approaches negative infinity. In other words, as we go to the left, well, once again, the function's pointing down. So we would say q of x approaches negative infinity. Okay, so that's when they talk about end behavior. That's what we want to see. We want to see what happens when we go to the right, what happens when we go to the left. Okay, let's look at another one here. We have 2x to the fifth. So we know that our leading coefficient is positive and that our degree is 5. So it's going to be that oh no you didn't girlfriend graph. There it is right there. It just has an extra hump in there. All right, so we have that. So now I want to describe the end behavior. So as x approaches positive infinity, as we're going to the right, you can see that it's pointed upward. So we would say that p of x approaches positive infinity. And then as x approaches negative infinity, well, that's when we're going to the left, it's going down. So we would say p of x approaches negative infinity. Yeah, we could say left, right, up, and down, but this is mathematically is a little bit more of an appropriate way of doing it. So, all right, there'll be some problems for you to work on there. Now, the other thing is that we're going to look at is we want you to be able to look at a graph and you decide if it's odd or even and if it's got a positive or negative leading coefficient. All right, so now, the way to tell is on a graph like this. They're pointed in opposite. Opposite, think odd. Odd, opposite. All right, so this is an odd degree. And because we're going left to right, if we're going down, that means it's going to be a negative coefficient if it's going downward. So we would say odd and negative is what we would say there. All right, now this graph, you can see that they're both pointed upward. Well, when they're both pointing in the same direction, that means it's even. Okay, and because it's pointed up, well, they're both positive, that means the leading coefficient has to be positive. So we would say even positive is what we would say there. All right, a couple more here. All right, this one, again, we're pointed in opposite directions, so it's odd. And since we're going down, and behavior going left to right is going down, we would say that it's negative, is what we have there. All right, one last concept for 6-7. It's going to talk about turning points. Now, sometimes the graph, as we've kind of seen in some of these graphs, there's multiple locations. Maybe it doesn't have an actual minimum or maximum, but locally it does. And so we want to be able to identify those. We call those turning points when the graph hits and turns and goes a different direction. We want to identify those as a local maximum or minimum. It may not be the smallest or largest point on the graph, but in that area it is. And so we can find those by graphing. Let's say that we take this one here. This graph here is a cubic, and so on a calculator we want to see what the maximum and minimum are locally. Now this graph does not actually have an actual maximum or minimum. We'll just graph that on decimals here. I've got that hopefully posted. There we go. And here's the graph right here. Now you can see that this graph goes indefinitely down and then indefinitely up. So there is no maximum or minimum, but locally there is. You can see here this is a turning point right there. So if we just touch that, that will tell us what the local maximum is. Like I said, there isn't an actual maximum, but remember it's the y value we're looking for. So the local maximum here is at 21.785. All right, and then as we toot along here, we're going down. Well, this is a turning point here, so this is defined as a local minimum. Okay, like I said, there's no minimum of the graph, but locally, right there is. We can find that. Looks like it's right on -20, but let's double check. Maybe it's a little bit shy of that. Yeah, a little bit. So we would say the local minimum is -19.785. So again, graphing those, you can find those pretty easy. Desmos is our friend, and we should use that as often as we can for graphing. All right, well that takes care of 6-7. Try the worksheet. Again, check with the key. Make sure you kind of get those right. Again, send me questions if you got them. All right, so that's 6-7. All right, enjoy the week. We'll see you next time for 6-8.